All right, welcome everybody on this Wednesday after summer. It's September 11th, and this is going to be an Are Robotics community group meeting. And today is a presentation meeting. So usually what we've done before the summer and are still planning to do so is that every 2 weeks every 2 weeks we have a meeting, and interchangeably we have a presentation meeting and developer meeting. And for presentation meetings like today, we invite somebody to give a presentation about their cool work with drones or present their hardware, or in this case a paper, but I will explain a little bit more about that in a minute. So that's exactly the agenda that I've already explained. So a couple of announcements. So it seems that the Gazebo ionic test and tutorial part is still ongoing, but they need quite a lot of help. Especially from Windows and Mac users. So if you happen to have a little bit of time and a Windows and a Mac, make sure to help out. Especially the Windows build was difficult. I managed to do it, so if I am able to do it, you guys are definitely able to do it. But there were still like 177 issues open. I'm not able to do that by myself, and I don't have so yeah. So the deadline is for that is this Friday, which is Friday the 13th. And also Roscono Dance is coming up very soon. So that's in the 21st and 23rd of October. BitGrace is going, so we'll have a cage of crazy flies over there. Let's see if we're the only drone company over there. But of course, don't forget that at least the early bird has already ended, but I think at the end of this month you can still have the medium price jacket, let's say. Before I continue, does anybody have any events that they would like to share, or any package that they've been working on? Let's say you can open up your microphone and you can just shout it out at this moment, just before we start with the presentation. I don't know if anybody has an announcement on that.
ROSCON in Bangalore is happening 5th, 6th December. They haven't announced, or ROSCON India actually, they haven't, I think, shared the link for booking, but they've just announced the dates as of now. And I've been messing around with Aerostack 2. I think I saw the RSS24 demo right now and I was trying to get it to work. I faced some hiccups. But in general, I've been going through the documentation, looking through the test cases and getting myself familiar with the framework, so that for indoor navigation, if you want to add something like VIO, how that would exactly fit in, as I think it'll fit in at the spot where they have the Aruco detector plugin. So I'm getting a sense of the overall architecture, because it's a slightly complex stack. It's just unfamiliar at this point. So I'm just diving through the code base and understanding all of those things.
All right. Thanks a lot. Can you share at least the names in the chat so that the others can at least see? And but yeah, of course, Roscon in Bangalore. I think Roscon Germany is also soon coming up. So those are local ones, the ones that I haven't listed there. But I think if you follow the ROS Discourse, there's definitely a lot of things in there. Anybody else has a short announcement or not? I will continue to the next slide. Oh yeah, just a very quick reminder. Before the summer already, we open up the ROS, the Aerial Robotic Landscape, which is a website where we place information, which is the kind of an information hub for anything that's related to aerial robotics, to different courses, hardware, things like that. I've added a couple of things myself together with Alexis. To kind of keep it up to date. But of course, this is kind of a joint effort. So make sure if your hardware is not included, or if you have just put a course online about aerial robotics, make sure to add that. You can just edit it in GitHub. All right. So next up is a presentation by Giuseppe Silano. And the presentation name is Are Robotic Simulators solve problem criteria for selection and customization? Giuseppe is an associate researcher at the Czech Technical University in Prague. And yeah, it's pretty much about a survey paper that I've written together with Giuseppe and definitely several others, but I'll leave all the explanation up to him. So yeah, go ahead. I'll close my presentation and you can go ahead and share yours.
Thank you, Kimberly, for the introduction. Let me share the screen. Just 1 second. Okay, let me see. Yeah, I can see the slides here. Okay, please feel free to interrupt me if for any reason there is a problem with the slides or you cannot see my screen and so on. So everything.
Of course, yeah.
Sorry, not this one, but this one. Okay, nice. As Kimberly said,
we lost your slides again.
No. Okay, let's do. I was aware of this issue. Okay, so let's do like that. I mean, these days, yes. I hope that I will not receive so many notifications. So sorry for that.
No worries. Yeah,
okay,
now I see it again.
Okay, so as Kimberly said, today's talk, I will, let's say, present the results of the survey that recently got published on IEEE Robotics and Automation magazine. And from that, I extracted this talk, where the aim is not, of course, to present everything that is included in this survey, because it's very long, and also it's not the aim of the presentation, but to give you some hints on how a robotic simulator should be selected, which one is the best one for a specific application that can be machine learning based, can be dynamic based, or and so on. So this is why the title of this talk is the choice of a robotic simulator a solved problem, okay, or there is still something that needs to be done. Let's do this. Let's see this during this presentation. So first, let me introduce a bit myself. This will not take too much time. I'll just introduce about my experience and why we decide also to meet with Kimberly and the others to first organize a workshop where we discuss this topic and then come out with a survey. I start my, let's say, academic research at the University of Sangio. It's a very small university in Italy, close to Naples. There, I've been working on software-in-the-loop methodologies for testing the control algorithms of multi-rotors. Then I moved to CNRS in France, where I also have continued working on multi-robot. But there I joined also the MB Zirco competition. It was the 2020 edition. I don't know if you know it. It's a very important competition worldwide. And there I faced the issue and the importance of working with robotic simulators, because you know, when there is a challenge, so this means that you have robots that have to face a really complex problem and also to have to react to the environment, and in a simulator where you can test what you expect to have in reality, it's very helpful. After that, after, let's say, this sort of parenthesis, I came back, defended my thesis, and decided to join. I mean, there was the opportunity to be a postdoc at the Czech Technical University in Prague, and I came there. There instead, again, the use of a robotic simulator, but here I also discovered important to have a flight stack. What does it mean, a flight stack? Means that you don't have only the simulator where you can test your algorithm that can be written in C++, Python, whatever, but also the important of being sure that when you are going to test the algorithm, the firmware that is running on the robot is the same that you will have. I mean, the simulation is the same that you will have in reality. This makes sure that if you see that the drone is behaving in a certain way, I mean, aside external forces that can act on the robot as wind gust or noise generated by some sensors, the behavior it's pretty much the same. Then, after this period, I went back to Italy, where now I am. I'm a tenure researcher in a public control research organization. It's called RSC. And also during my career, I've been visiting researcher at the University of Twente, where I had the opportunity to work with Antonio Franchi on a platform, let's say, that are not standard multi-rotors. This means omnidirectional platform, full actuated multi-rotor, and so on. So just one slide. I don't want to abuse of this, let's say, this talk for promoting the group. Here, just to say what is the MRS group. Here there is QR code that you can scan just to visit the web page. The group was born in 2015 with the 3 employees, and then after a while, let's say during time, he grew up, and now it's more than 30 employees. And the main focus is on motion and trajectory planning, control and simulation, and computer vision. So let me now just stop for a second, because I would like to show you this video where you can see, let's say, a very nice animation. I don't know if you can hear the sound or it's covered by my voice, but what you are, let's say, looking at, it's Agile Flight. It's the current topic that MRS is focused on. And the main topic there is to, let's say, push the boundaries of making the platform able to fly at very fast speed. And this is, of course, is not challenging from a hardware perspective, but also from a robotics perspective, simulation perspective, because you need a simulator that's capable of accounting for the aerodynamics effects that, while they are negligible when we fly at low speed, they become really, really important when we are flying at high velocity. So now let's talk about let's say, the survey. I will not bother you anymore with the other type of information. So here is the outline of the presentation. What I did is to try to, let's say, cover the paper itself, starting from a very brief introduction. There is a question that we came out and that we use for, let's say, collecting information about the simulator, the UAV simulators that we found out, and the features that are related to them. Finally, the discussion that came out from the workshop that we organized in 2023 at ICRA in London, and some general conclusion after this discussion, this talk. So, as you know, I mean, we are part of this area robotics community. Nowadays, UAVs are very popular. They use not only in industries, but also for precision agriculture scenario, in inspection and planning. For example, they are used for inspecting civilian infrastructure, such as power line. They use it for mapping, if you know about DARPA competition. So these robots that are capable of navigating a cave, and also for search and rescue operation. Now, what's the really challenge right now is that when we go on the field, we see that unexpected behavior that we can encounter, because we have these simulators, they are really nice, but then we move in reality and we see strange behaviors of the drone. So the simulator becomes really a core of our research, because it's a tool that allows us to test the algorithm deeply, and if for a reason or another this tool it's not close to reality, this can be a problem, because for many reasons. First of all, crashes can be in high cost. I mean, a drone is not a cheap device, so this means that if we crash, we can destroy the hardware, not only so the controller itself, like the autopilot or like the X4, but also the mini PC that is on the UAV. If we think about the platform that are quite big, like say in the order of kilos that goes from 1 to 5. Also, it can disrupt our let's say, experiments, because imagine that we are performing experiment on the field, and for a reason or another, suddenly the UAV crashes. This means that we will take, let's say, up to 5-4 hours. It depends on the type of damage to repair the UAV, so to continue the experiments. And then this is something that we never have to forget. This can be dangerous for, let's say, the environment, our planet, because what we do is to frequent the replacement of components like propellers or plastic parts that build the framework. So the question is, which simulator should I choose for testing my algorithm? But also another let's say question, very important, is why this is the right simulator, and which one is the best for my specific application. These are all kind of questions that we aim to answer with this presentation. So as I said, in 2023 with Kimberly and Wolfgang Honing from to Berlin, Chiara Gabelleri from Twente. We held a workshop titled The Role of Robotic Simulator for Unmanned Aerial Vehicles at ICRA. So what was the purpose, the aim of this workshop? To gather insight from the scientific community and reach a consensus on the most suitable simulator. Here on the right side of the slide, you can see how many people attended this workshop. So just to let you know how sensitive is the topic. What we came out is that of reaching a consensus, we saw that we discovered that there are 16 completely different simulators, the most used one, of course, and each one is tailored for a specific use. So we decided to go to the next step. Write down a survey, describe these simulators, understand which one is the most suitable for each specific application, which are the vehicles that can be simulated, multi-rotors, fixed-wing aircraft, and also the amount of sensors that itself are emulated in these simulators. So there's this question. What criteria and consideration should guide the selection and customization of a simulator to optimize its suitability for a specific application, and while also understanding its limitation? This was the main question that prompted us to, let's say, write the simulation, and this is what we try to answer in this survey. You can find the reference in the bottom of this slide. So before starting, of course, the writing process, we went across the literature. We tried to see what were the survey that were available at the time, and also understand the topic. For example, they only describe standard multi-rotors, or they lack the support of these. And generally, what we saw is that the aerial dynamics differ significantly in this simulator, depending if we are simulating ground vehicles or we are simulating aerial vehicles, because of course these some of them are general purpose, and we also find out that some of them neglect the aerodynamics effects. So the key contribution of the surveys focus on writing a survey that was able not only to describe the simulation, but also the aim was to exploit our experience and the experience of the people that at the talk, at the workshop, that participated in many robotics competition and carried out a huge amount of experiments on the field to guide the selection of the simulator. And also, the aim was also to come out at the end of this discussion with a sort of, let's say, guidelines that should help in designing the new simulators, what we expect from the features, collecting feedback from senior researchers, developers, and also from early career professionals. These were the key contribution of the survey. So, simulation criteria. Of course, everything is application domain, as I said many times so far. And the simulator, we need to understand what are the features that are and the sensors that are tailored for our specific application, and also what are the control unit that we are able to emulate, okay, in this case, Pixel4 R2Pilot, and if there are specific platforms such as Crazyfly from Bitgrace that we are also capable of emulating with this, simulating with this platform, because I mean it's okay, it's nice to work with a big platform. I mean, as I said, these very huge vehicles, but from time to time, and also I mean we are constrained by the environment, by the university, or by the weather, because we cannot carry out experiment outdoors. So we need to rely on some, let's say, multi-rotors that we can test in a very small environment, as the Crazyfly allows to do. So here are some criteria. So I will spend a bit of time on this. We saw that criteria are physical fidelity. What does it mean? Is the capability of the simulator to describe the physics and the physics of the environment, and also the dynamics of the multimotors in a very detailed way. Also, what is really important is the visual fidelity. What does it mean? It means that the level of realism in images, and this is very important for computer vision and machine learning applications, the capability of simulating or reflecting the behavior of autopilots such as autopilot and Pix4. This is very useful for what concerns the software in the loop and the hardware in the loop testing. The capability of this simulator to emulate multiple vehicles. Imagine that we would like to perform or we would like to work with swarm of robots. So this is very, very important, having a tool that is capable of simulating from a couple to 100 of vehicles. The heterogeneity. What does it mean? It means that we can simulate different platforms, such as a standard multi-rotor, so a quad rotor, but also an omnidirectional platform, but also a fully articulated platform, but also a fixed wing vehicle. And the sensors that we are able to emulate. This means an IMU, a GPS, the behavior of a LiDAR that can be 2D or 3D, the optical flow, and the UAV models, as already said. Another important aspect is the simulation speed, because learning is exploding. So what we see in academia is that there are simulators that are capable of simulating, hundreds of robots. So this makes this the training process very, very fast, and this is important for this type of application. The possibility to use APIs, so this means that we can use many programming languages in order to interact with them, and how easy is to move from the simulator to the real world experiments. So here it comes a bit the concept of flight stack, but we will reach this step by step during this presentation. So these were the criteria and the decision factors behind these criteria that we selected in our study. Let's now, before let's say I go deep in the discussion, what I want to do here, I took some of these criteria, okay, and I try to pass from the simulation, sort of highlighting some key aspects, and also give you some example of which one is the, let's say, from our course study that best can be seen as a physics fidelity simulator, visual fidelity simulator, and so on. These are just a few slides just to give you some, let's say, practical example of what we are talking about. So as I said, physics fidelity is a simulator that it's capable of deeply simulate the physics, so the dynamics of the multi-rotor of the aerial vehicle. And this means that we not only can simulate aerodynamics, but also collision detection, rotor dynamics, okay? And simulators like that are Gazebo with RotorS and Flightmare, just to give you a few examples. And these are used for accurate physics, such as agile flight, air manipulation, or payload transport. Then let's jump to the other, let's say, criteria, that in this case is visual fidelity. So as we said, this is a simulator that is capable of closely simulate, the real of the visual environment in the simulator. This means that the graphics is of high quality. during the simulation. This is very useful instead for all the applications that involve vision, such as flame, object detection, gesture recognition, and example of these simulators are all the NVIDIA's like simulator, such as Isaac Sim, Are Sim. They are very quite known for this photorealistic rendering, and these make all these kind of simulators very helpful for all machine-related applications. So continuing with this, another criteria, very common, it's the simulation speed. In here, the key aspects are related to the real-time performance and the scalability. Real-time performance, this means that they are important for hardware-in-the-loop testing, and this means that the simulator is used for real-world time, and also the scalability. This means the ability to handle simulation with multiple UAVs, so swarming, or complex environment without significant, let's say, slow down the simulation. If some of you have experience with Gazebo, on the top of on the bottom part of the simulator, there is this real-time factor. So what we do when we run a simulation is try to keep this factor as close as possible to 1. Example for this, let's say, simulation speed simulator are flight Googles. This simulator is optimized for high-speed simulation and suitable for testing swarm of robot and also fast algorithm iterations. And there is also Potato. These use the GPU acceleration for large-scale swarm simulation, maintaining speed even in the case there is a numerous amount of agents. Let's continue here with the UAV models. UAV models, so the capability to simulate by various types of UAV, from multi-rotors to fixed-wing drones. Key aspect in this case are the flexibility, I mean the amount of drones that can I simulate, and also the dynamic modeling, the capability to represent different flight dynamics for various UAV configuration. So in this case, we are referring to these fully actuated and omnidirectional platforms. Example of these simulators, it's ROS and Gazebo, of course, if we are talking about multi-rotor vehicles, X-plane and flight gear in the case that we are referring to these fixed-wing vehicles. Just last one, and then I will, let's say, be more practical with an example. Let's talk about the integration. As I said previously, it's not only important to be able to simulate a drone, to simulate the sensors that equip the drone, but also the capability to move from simulation to real-world experiments. So in this case, the capability to support autopilots, this means that we can simulate the firmware that is running on board the flight controller, okay, and also the capability to integrate the firmware, as I said, for software and hardware-in-the-loop tests. Examples for this, again, Gazebo with the Pix4 software-in-the-loop integration, Autopilot with the software-in-the-loop integration with Gazebo, AirSim, this simulator provides some APIs for data retrieval and vehicle control. And then if we are referring to the Crazy Fly, we can find Crazy Sport 2, which integrates those two for controlling large indoor quadrotor squads. So now that we saw, let's say, I mean, I was a little bit fast. I know that I have a lot of information, but then there will be the discussion part where we will try to, let's say, sort of recap what I said during this presentation. Previously, we saw the criteria, okay, how we sort of understood what are the criteria and their its definition, okay, their definition. Here instead, what we did is to sort of classify, categorize the UAV simulators. This means that we came out with 7, 8 categories. Universal simulators. These are simulators for multiple platforms. This means ground vehicle, aerial vehicles, and so on. Underwater vehicles. Sensor focus simulator. This means all the simulators that are allows to simulate sensor with very realistic performances. So for photorealism, LiDAR, and so on. Learning phase simulator. This means all the simulators that allow to train machine learning algorithms in a short time. Let's use this word. Then dynamics focus simulator. So this means that we not only can simulate the behavior of a quadrotors, but also we can simulate some aerial manipulation. We can simulate fixed wing vehicles. We can simulate also not standard, let's say, platforms such as fully actuated platform and omnidirectional platform. Then there are swarming-based simulators. This means that all the simulators that allow us to simulate up to 20, 30, 50 multirotors. This means that we are focusing on this swarm of drones that can navigate an environment and creating a map, for example. Then part of LESTEC, as I said, the importance of getting a simulator that not only it's capable of describing well the dynamics of the robot, but also the firmware of the flight control unit that we will use in reality, and this makes the test really powerful. Because I mean, we are pretty sure that there will be no numerical instability due to some libraries or some commands that are, let's say, do not respect the boundaries of the flight control unit, or just let's say because we didn't map the angles from minus pi over 2 to plus pi over 2 to I mean, let me explain me better. We didn't map this minus plus pi over 2 in the range plus minus 1. And then what else? Flight simulators. This means typically for large-scale human pilot aircraft adapted for some robotics applications. So here on the right side of this slide, we can see how from these categories we came up with this list of simulators. So from the universal simulators, as I said previously with the example, we saw Gazebo Classic. This means RotorS. Let's say kind of first robotic simulator for multirotors UAV. It was around 2040 with ROS Indigo, if I'm not mistaken. Then Crazy S, this is my own contribution that I will use for make you an example during these slides, and was meant for simulating the behavior of the Crazy Fly. At that time, it was Crazy Fly 1.0, and the first Crazy Fly that was moving from a plus to a cross configuration. Then here we can see also webbots, Coppelia Sim, formerly VREP, and so on. Instead, in the sensor focus simulator, we can see, depending on if we are focusing on vision or on the use of LiDAR, AirSim, Flightmare, FlightGoogle's Flightmare, if you know it. It's the simulator from Davide Scaramuzza's lab. And they use a lot with this event-based camera and for machine learning application. Then we see the learning focus simulator. Here we can find Isaac Gym, again, Flightmare, Safe Control Gym, and so on. Among the dynamics focused simulator, we can have the MATLAB UAV toolbox. I mean, even if MATLAB, I mean, let's see him as an outsider, because you know MATLAB it's a commercial tool. Recently, they come out with this nice toolbox for emulating the UAV dynamics and also the controller. There are also on the MathWorks website some really guidelines where you can see the use of powered drones. I mean, it cannot be compared at the moment with other simulators such as Gazebo, okay, but it's very useful if you are starting from scratch or if you have a very small environment and would like to play with these powered devices. Then swarming, so GIM pipe bullet drones and quad swarm potato. Part of flight stack, we can find Agilus, that is the flight stack from Davide Scaramuzza's lab. The MRS UAV system, that is the flight stack from the Czech Technical University in Prague, the multi-robot system group, the group that I introduced at the beginning of my presentation. Then we can find a couple of tools that work with the Crazy Fly, Crazy Choir from the University of Bologna, and the Crazy Swarm 2. That is, I mean, the first version was developed by Wolfgang Koning, now at Berlin. This second edition, I know that Kimberly and Wolfgang and perhaps others are working on it. Then for the flight simulator, so this means fixed wing devices, we can find X-plane, Q-plane, flight gear, and so on. So here the categories and also the simulators that we sort of try to cluster within these categories. So with this table, I know that is very dense and rich. What I try to do is to remove some information, and because I mean on the survey that you will find other more information for the simulators. Here, what we try to do is to sort of select the most used one and try to emphasize the physics engine, the rendering, the interfaces, if they are, let's say, software adapter in the loop platform, the license, because this is very, very important. I mean, seems to be like not a subject, I mean, a subject that nobody cares, but instead the license is very, can be tricky, because I mean, depending on the type of license another, we could, let's say, be obliged to, if we come out with a contribution to make it open source, or we cannot, let's say, to that, or I mean, there are some constraints we should be careful. Also, if the simulator is open source, and if the simulator is actively maintained. What do you see in the literature is that from, I mean, the academia, it's producing simulators often, okay, but after a while, because behind the simulator there was a PhD student, or because there was a project behind the simulator was meant for a specific application, or simply because the research group is moving from a topic to another, this simulator stopped to be maintained. This means that since ROS is evolving, the most used middleware for working with robot, let's say from ROS 1 to ROS 2 can be a simple example. The simulator is no longer maintained, and this, let's say, it's a very something that we should have in mind when we select a simulator. So, as you can see, Gazebo is the most, I mean, the one that has the most physics engine that we can select. While if we see the others, another one is Copelia Sim, that formerly was VREP. And as we can see, I hope that you can see my mouse. Here we can find, for example, Flightmare that uses an ad hoc physics engine, but also Gazebo Classic. And if we jump to the column of the interfaces, again, most of them are ROS 1 and ROS 2 compatible. Python and C++ are other, let's say, programming language well connected to these simulators. From time to time, we can see Java, Octave, Lua. These are, let's say, very old scripts that work with the simulator. This one, C#, but I mean, it's not so well common to find it. And as for the MATLAB UAV toolbox, of course, we find MATLAB as an interface. Instead, if we go to the software Arduino group, we can see that here, I mean, the platform, I mean, are not so that common. We can find Pixel 4, Autopilot, and CrazyFly, but in others, as you can see, there is no information. I mean, there is no support for them. And if we jump to the licenses, we can see MIT, okay, GNU, and some Apache license. This is just to try to comment this table a bit, just to give you some hints on the simulators. In these two tables, instead, we can see now how the simulators itself differ from the capability of simulating multirotors, helicopter, fixed-wing vehicles, to simulate aerial manipulation, swarms, other vehicles such as cars, or other systems in general. So here what we can see that most of them are able to simulate what is considered the basic multirotors, but when we jump to the, let's say, sort of drag effect, we can see that not all the simulators are capable of doing this. This is even worse when we try to simulate some external forces that act on the multirotor, such as wing. The orange star means that is only partially covered, and the situation goes worse and worse and worse. I mean, when we jump from the helicopters, fixed wing, aerial manipulation, and so on. The same goes for the amount of sensors. I mean, if we, let's say, use sensors like RGB, depth camera, point cloud, AMU, we can see that most of them is covered by the simulators. But instead, if we are trying to simulate a barometer or the optical flow or the GPS itself, this is not, let's say, something that we can find everywhere. So here, as I said at the beginning, there are a lot of information that I show you so far. I know that takes time to digest, and also you need to read carefully the description. So the idea behind the simulation is not to show you a table after table and try to comment this, but just to show, just to tell you about my own experience on selecting a simulator. And this guided us in proposing this workshop at ICRA, and also in writing this survey. So why we are taking a step back, as I said, a lot of simulators, the journey, this is something that I already said, I already told you. And the takeaway message is, okay, the goal is not to memorize with this presentation, with set of slides, all the possible simulators that exist, because I mean, this will be just a snapshot of today, but then tomorrow there will be other simulation, or the feature itself are evolving. So this means that, I mean, we cannot try to answer to all the question. What I want to do, what we try to do with the survey itself was to give you the tools for selecting a simulator. So when you will read the documentation, when you will come across a publication, you will understand if this simulation suits you, what are the features that you should look like, why this should fit your application, and so on. So let me talk about this CrazyS. CrazyS, born around 2018. As I said, that was the moment when the CrazyFly was the 1.0 version of the vehicle, moved from a plus to a cross configuration. At that moment, the only simulator, I mean, there was another one, I don't remember actually the name, but I mean, was not so much used. And ROS was at the version release of 14.04, okay, so Indigo, if I'm not mistaken. And RotorS from ETH Zurich was the only simulator available at the moment. So my needs were of simulating the behavior of this nice platform, the Crazy Fly. That, I mean, it's a very teeny device. You can fly almost everywhere. I mean, a very small indoor environment, but requires a very powerful controller, because as soon as you try to generate some thrust with the propellers, we will literally jump and you can destroy. I mean, it's a very powerful device, but also very easy to destroy, especially the propellers. So what I try to do is, okay, how I can face my challenge, how I can simulate the behavior of the Crazy Fly is already available. It's easy to simulate. What are the parameters that I should account for when I want to simulate this device? For example, the size of the propeller, the parameters of the motor, the inertia of the vehicle. And I found that at the moment in the literature, there were several works that try to identify the parameters of this device with some identification process, but nobody take, let's say, the responsibility or investigate the problem of having a simulator capable of emulating this platform. So I said, okay, let's build on my own. And this is how Crazy S was born. So there, what I did was, let's say, start from RotorS, create, let's say, a separate model for my vehicle. This means with sacrifice describing all the parameters of the vehicle, also importing the CAD of the Crazy Fly, and try to not only design my home controller but also import the firmware. So I went on the GitHub repository of BitCraze, download the firmware, and add the firmware inside my simulator. So this allowed me to simulate the Crazy Fly, as you can see here on this screen. So here, not only the controller that was a very simple PID controller for an hovering example application, but also the firmware that was running on board, the command filter that was used for combining the data from the view and so on. And this is how the simulator was born. So just to tell you how critical can be designing a simulator when there is nothing available. It's not, I mean, as it is now, and how it's important to know what are the simulators, because I mean, in case I was interested in simulating some machine learning techniques, so in this case, Gazebo, that was was the platform used for this simulator. I mean, the robotic simulator used for simulating the behavior of the Crazy Fly was, I mean, for machine learning application is not the best one. So this means that I should move from the ones that we saw so far, and also for other applications. Imagine that the Crazy Fly, where I would like to also emulate some external forces are acting on it. This means that perhaps the Gazebo Classic is not the best simulator for this. So here, the question that, I mean, that is written here, but instead of for myself, it's more for yourself and also for starting a discussion later on, is that, okay, imagine that now you will have the survey. Which simulator would you have chosen differently from the one that I have been using for designing Crazy S? So this means Gazebo Classic. This is the question that I will leave for later on discussion. And here it answers, let's say, the last part of my presentation, when I would like to present you the discussion that follow up our, let's say, workshop, where first speakers such as Davide Scaramuzza, Angela Swelling, and others help, and also discussing with the people that attended the workshop. What we try to do is to come up with some, let's say, bullet points, some, let's say, topics that we should consider when we want to design a simulator for the future and also select a simulator. So first of all, the application, the platform and the application are really a key in this case, because I mean, the choice of a simulator or another depend on for which purpose we are going to use it. And also another, let's say, important part is balancing between exploring multiple simulators and the need for some standardization. So the key identified themes were the role of dynamics in aerodynamics in simulation, the need for benchmarking and standardization, the difference between academia and industry, okay, the need for data sharing and collaboration, and the challenging in maintaining a simulator. So we saw the importance of aerodynamics effects, because in some scenario this is very, very critical, because we need to model the ground effects. If we think about tiny quadrotors, such as the crazy fly, this can be a very important problem, because the inertia of this vehicle is not so that high. Instead, we are talking about, let's say, very heavy drones that are not flying close to the ground, perhaps it's not so that important, or for example, for fixed wing vehicles is less important than for multi-rotors and so on. But this is an important aspect that we should have in simulators. What else? The need for a unified framework. So we need to enhance the reproducibility of the experiments, as perhaps you have seen in one of the recent paper of Angela Schweling on the control system, IEEE Control System magazine. She tried to analyze how many papers were published in the major conferences, the flagship conferences in control and robotics, and how many of the results that are shown in the papers can be reproduced. So the code, for example, is available on GitHub. And what we also need to address is the versatility of the universal simulators that allow us not only for concentrating our efforts on multi-rotors, but also other kind of vehicles, such as ground vehicles. An example can be a car, for example. So the new class of simulators should integrate this aerodynamics modeling, and also these should try to reply to the lack of standard benchmarking and practice, because I mean, comparing a simulator, comparing to a simulator without a standard benchmark can be very tricky, because it's platform dependent, depends on the PC that we are using for performing the test, also depends on the operating system. I mean, there are many factors that influence this benchmarking process. So having some standardization on this matter would allow us to sort of not rank, but at least sort of say, okay, assigning some scores on the simulators. Then difference between academia and industry. For academic simulators are very important for research advancement, but face the sustainability issues of development. What does it mean? It means that, as I said at the beginning of the presentation, in most of the case, the simulators are designed by developed by PhD students. This means that after the PhD, most of them, I mean, a very important part of them leave academia. This means that the simulator is no longer supported, and we cannot use it, because I mean, simple jumping from ROS 1 to ROS 2, we cannot, let's say, port, because this can be very time expensive for us doing that. On the other hand, the industrial simulator, they are really a robust support. I mean, there is a company behind them. They are very documented, and they follow a continuous evolution. This is more or less the difference between the two. Also, what we should do as a future goal, try to balance a bit these two words, because I mean, we should try to, the future simulator should try to, let's say, keep track of the innovation that we find in academia, and at the same time have the government support. And also, what is really, really important is the collaboration, because we are talking about stuff that really takes a lot of time, a lot of effort. There is the knowledge that you need for designing this. So data sharing, collaboration, supporting project on GitHub, as Kimberly mentioned at the beginning of this session, it's really, really important. It's key in this problem. Challenge for newcomers. When you are new to this world, imagine that you are starting your PhD, or you are, let's say, working on your master thesis. Most of the time, you don't know anything about the simulators. So you face the problem that these simulators are not documented. This means that you come across a GitHub repository. Yes, okay, there are some information, there are some instructions how to install it, but then there is nothing about how it works, the sense that you can simulate the dynamics that is associated, if there is some noise and so on. And what else? Really, really important, as I said, the licensing, because I mean, this impact the utility, adaptability, and ability to modify the simulator. Because if, of course, a simulator is a proprietary, we cannot, let's say, we cannot improve it. If it's open, yes, I mean, depends on the license. I don't want to comment now all the type of licensing that there exists, like MIT, GNU, also the version of the releases of GNU, like 1, 2, 3, and so on. But this is a very another important point that we should take into account when we design a simulator and we want to make it available for the others. So here I want to conclude this talk. I mean, I don't have the time, but I think that I spoke for a very long time. And what we saw during this talk was, let's say, the challenge and the reward on selecting the right simulator, and how we can enhance the safety and reduce the testing time and costs. Also, what I tried to do was, let's say, sort of present an overview of the robotic simulators and that are currently available for aerial vehicles. Also, what are the decision factors? Also, we saw the criteria, we saw also how we cluster the simulators, so the universal simulator, learning-based simulators, sensor-focused simulators, and so on. And also the recommendation for new researchers. I mean, the outcome of the discussion, the key points, such as the aerodynamics, the importance of licensing, also the importance of documentation, and so on. And what's really very important, I know that this is the last bullet point of this presentation, but the community value, because I mean, this is very important for guiding researchers in aerial vehicle research and simulator selection. So these some acknowledgements. As you can see, this was the team that was working on the simulator, and also on the workshop that we held in ICRA, at ICRA in London. Also the people that took part of their time to revising our survey. So very special thanks to them, and the project that supported the work. So this concludes my presentation. I hope that you enjoyed my talk. I was enough clear to explain our findings. Now, let's say a question for the discussion. Is this the issue really solved? I mean, after, let's say, after you saw the presentation, so all the robotic simulators that are available so far, are the criteria for selection and customization enough? Can we consider the problem solved so far, or still it's something that needs some investigation? Thanks.
Thank you so much, Giuseppe. That was a really interesting, very interesting presentation. And I didn't mind it being too long because there's a lot of very useful information, but I do hope that we might want to keep the question part a little bit short to just kind of wrap up within an hour. Does anybody have any question for Giuseppe or something that I can maybe also help out with answering about the paper? Mayank, go for it.
Okay, so
all right, maybe I'll start. Okay, I had a comment. So for the academia versus industry, as far as I know, some of these simulators allow for plugins. So would it not be better for academia to contribute self-contained plugins for the gaps that they identify instead of trying to roll out a full-fledged simulator, which you know is going to die a slow death? Couldn't that not be a sustainable approach? That way, the bulk of development and maintaining the simulator is like an industry pursuit, but maybe specific areas of research which some research group is trying to target could potentially go in, or in your understanding of how these simulators are written and structured, that's like a fool's errand. Like, what are your thoughts on that?
This is a very good question. Very good question. I mean, I'm not so expert, let's say, with the plugins. Perhaps Kimberly is more, so can answer to this question. But definitely, yes. I mean, this can be a good compromise. Kimberly, what do you think about?
I think there are two problems. Let's say that's why academia are just using or making their own process simulation from scratch. I think it's partly the fact that they are not very much aware of what these capabilities of the simulators are or how flexible these plugins are. It's also kind of a limitation of what they can actually code. So like, for instance, Gazebo has their plugins in C++. I know that they have Python binding since of recent, but that's very new, and it kind of requires quite a big development process. Then you would rather want to build a simulator, for instance, in the language that you know. And second is, I guess, like perhaps the availability for documentation. But yeah, there's also kind of like, yeah, usually there is a lot of documentation, but it's like where can you find it? And of course, citations is also very important. If you've made a simulator and a lot of people are using it, then of course you get a lot of citations also in your paper as well. So it's, yeah, I think that those are kind of like a couple of aspects of it that makes it a bit difficult to convince academia to, or academics or researchers to actually build plugins. But you know, you have some that do, like all of the simulators that Giuseppe has presented like sometimes are like, you know, for instance, like the peaks for hardware like software in the loop are kind of like that's connected to like that's made through a plugin for Gazebo. I don't know if you have anything you want to add to that, Giuseppe.
No. You were really clear. I mean, you said everything about this topic and the use of plugins. I mean, you touched the key point that, I mean, citation is also very, very important. You want the others to use them.
Yeah, exactly. Like you do need to get citations in order to
build
up your lab, right?
Yeah,
so,
exactly.
Yeah, I've been on both worlds, indeed. Okay, I'm just going to. I hope, Mayank, that answers your question. I'm going to give the word to the video now, and then.
Hi, thanks for the presentation. It was very interesting. I've seen a growing interest into robotics as a service. So within this context, which of these simulators would be better suited to be run in the cloud compared to a local machine?
It depends on the application, I mean, that you are referring to. In my opinion, I mean, on the cloud, you are talking about using them, for example, with a browser. I have a machine that is running my simulator, and then I'm accessing to this machine using a browser. Or do you mean, for example, use cloud computing for machine learning application? It depends really on the purpose, from my personal point of view.
Yeah, well, I was thinking about both actually. So which ones would be better suited to each?
Okay, so my whole experience whenever I try to use Google Cloud or, for example, other services for running a simulation with Gazebo, I mean, was really a mess because I mean, I was struggling, let's say, to move the mouse. You know, when you are using this Gazebo, you would like to watch around, or, for example, some zoom in, zoom out was really, I mean, a sort of, I can say. Really, it's like that when you are watching, when your internet connection is not good, and you see a frame, and then after a certain after a while another frame was scattering. I don't know if this is the right word in English to say this. And instead, for cloud computing, I mean, I don't have personal experience on machine learning, but I think that having a cloud for machine learning application is very powerful. And in that case, perhaps you don't need, let's say, the rendering part. So you are running, let's say, in a server mode. And of course, it's better than your own machine for this application. This, of course, is for my bit of experience. I really don't have so that much on learning.
I hope that at one point Google Stadia will come back for robotic simulations. It was awesome. Why not? Like perhaps the gaming industry has a couple of examples for at least high fidelity in the cloud.
You could simulate Stadia?
Sorry?
Sorry, you could simulate on Google Stadia?
No, you cannot. Or well, like you can play games on it, but it's dead because it has been Googled. So it's just as a thought, maybe like Google Stadia. I just have to I hope that your question is answered.
Yes, thank you.
Yeah. Okay. Awesome. I'm just going to give it's the last question. So if the one who put the hand up, yeah, you can share your question. You have a very long name. I afraid for it, but go for it. You can just unmute yourself and say it.
Yeah, I'm audible, right?
Yes,
Hi.
we can hear you.
It's a great to listen you. Actually, students who's more interested to state estimation, lead controller, and all. So, can you suggest some simulator which you have seen, which can be worked in that phase, like going to top down to the firmware side, not exactly where I can see, but in Python, if it able to, some students can able to do which state estimation and lead control, and is it any simulation there, or we have to create some plugins for that?
Could you understand that, Giuseppe?
No, I didn't understand.
Shall I repeat it, perhaps? Like I hope I got it. I hope I got it right. I think he was asking like if there's any simulator that you would recommend for more lower end type of like state estimation, for instance, or like perhaps like I would put control on that. I believe like if there's the the robotic simulators that actually is able to simulate it is more suitable for it.
I think that's the most suitable one is Gazebo, but then of course depends on the application. So I mean, if you are just simulating the behavior of a multi-rotor or let's say, a multi-rotor Gazebo can be okay, but then if you are focusing your attention on other platforms, another simulator can be the best. Or if you are, let's say, working on learning, then you need to focus on this NVIDIA simulator. I mean, that really depends on the application, because the control and state estimation are really, let's say, sort of basic components of every, let's say, I mean, real-world application, not only aerial vehicles, but also, I mean, robots in general need control and state estimation. Depends also on the amount of sensors this
Yeah, I like to add, like, of course, you mentioned the software in the loop of PX4 and Autopilot with that's connected to Gazebo. Like, technically, I would say, indeed, those type of plugins that actually simulate, like, where you compile the code on the computer itself already have the state estimators and the controllers on them. So, yeah. Does that answer your question?
Yeah, thank you.
All right. Okay. Okay, I'm going to wrap it up because there's still a couple of things that I would like to show, and I know that you guys are all busy people with lives, at least the evening here. But thanks again, Giuseppe, a lot for this really great
thanks. Perhaps I was too long.
presentation.
I said a lot.
So make sure to read the paper, The Survey of Simulator for Aerial Robotics, an overview and in-depth systematic comparison. Hopefully it's not going to be already outdated next year, but maybe we can update it on the aerial robotics landscape. But it's we worked hard on this, so we definitely would like to have your feedback on it as well. Yeah, and I've added the links in the chat. So the next up is a developer meeting in 2 weeks, which is on the 25th of September, also 4 p.m. UTC, or if you're in Europe, it's like 6 p.m. Since we have been on a break for a really long time, not a lot has happened in terms of projects. So I think that will be a good moment for us to kind of discuss, reevaluate, perhaps look again at the projects that the subcommittees have been doing, and perhaps see something that we can work on together. I will send some messages to some of the co-leads, and I've also had some questions of people like, how can I join, how can I contribute? So I just would like them to wait a little bit longer and just join the meetings, and just try to join the meetings, and hopefully we'll have a little bit more contained projects that you can join for. But what you can help on now are the Gazebo Ionic tutorials, tutorial party. So that is, they also have drones in there. Please test out if the multicopter plugin is still working. So that is for 2 weeks, 25th of September on a Wednesday. We have the GitHub organization on here, and also again the ROS Robotics Area Landscape. Please add some information if you like. The slides of Giuseppe, I will end this recording. I will actually put on the ROS discourse, so that you can watch it again, or people have missed this. So yeah, thank you all for joining. It was a very busy meeting this time, so I'm very happy. All right, have a great evening, everybody.
You as well. Bye.